teach you how to make an explosive cup of coffee.
На нашем фронте самым старшим был сын Колумб.
Hello, I'm your host Ivan Ivanovich, and this is Famous Mathematicians. First of all, I'd like to thank our guest, Leonard Euler, for coming here today, as he has a very busy schedule. He's here to talk about his life and his contributions to calculus.
Hello.
Hello.
Oh, hello.
So, first of all, tell me about your childhood.
I was born on April 15th, 1707 in Basel, Switzerland. My father was Paul, my mother was Marguerite. My family is very religious, and I was raised in a home where everybody is involved with church. And so my mother was the daughter of a pastor, my father was a pastor, and my dad was friends with one of the Bernoulli brothers, which sparked my love for maths.
Okay, so you moved around a lot in your life. So why did you do this?
I started in Switzerland, moved to Russia, to Germany, and then finally to Russia. I started in Switzerland with a master's in philosophy, and in 1730 I moved to the St. Petersburg Academy, where I became a physics professor. After that time I moved to Berlin to work at the Berlin Academy of Science and Beaux Arts, but Frederick II, King of Prussia, would not give me the directorate of that, and I was very upset. Even though I was fit for the job, I did not get this. So I was displeased, so I moved back to Russia. And the problem is that at the same time, there were a lot of wars going on. The Russians, Prussians, which is now Germany, so I can interchange, and the Ottomans. Everybody is fighting each other or somebody else. So I was kind of moving around, running away from the wars as they happened, and I was trying to avoid all the chaos. Kings and queens fighting each other. There was lots of political problems in Europe at that time, but at the same time myself, the Bernoullis, Newton, all these great minds were coming together to advance maths.
Okay, let's talk about maths now. So, what's your identity theorem?
My identity formula, or theorem, is comprised of 5 of the most important mathematical concepts: E, I, the numbers 1 and 0. It is e to the power of I times pi, so e I pi, plus 1 equals 0. And when I discovered this formula, I realized that I connected everything. 3 unrelated subjects: the natural logarithm base, an imaginary number, and a constant used for calculating circle areas. And so by connecting these numbers into one formula, we've been able to do lots of things with it. It's used in electrical engineering for laws of capacitance and reactance, and it is used in Newton's gravitational law, and also for engineers trying to figure out things like radio station wavelengths.
Okay, so could you tell me about your findings on the Königsberg problem?
Ah yes, Königsberg problem. Well, I guess I didn't really solve it, I just proved it unsolvable. You see, the Königsberg problem basically suggested that there were 7 bridges connecting 2 islands and 2 mainlands in East Prussia, and that there was no way to cross all the bridges without crossing one twice. So I stopped looking at the bridges as unmovable straight lines, but instead I looked at each landmass being a point. So there's 1 island, 2 island, 1 mainland, and another mainland, and I connected all of them with curved lines, right? They each represent a crossing point bridge. And so each dot, or the points, had an odd number of connections, and because they're an odd number, that means that you cannot cross the bridge. That has to be an even number. And so the lesson learned was that I'm one smart pierogi, and that the odd number of connections, despite being able to move things around, created the inability to solve problem and cross each bridge once.
Describe your polynomial formula. What kind of polygons or polynomials were needed to fit it?
A polynomial formula, which is v minus e plus f equals 2, is basically a relationship formula comparing different parts of a polynomial. So let's take this polynomial for a second. a rectangular prism or cube, I don't know. So V, number of vertices or corners, 1, 2, 3, 4, 5, 6, 7, 8, minus number of edges, 1, 2, 3, 4, 5, 6, 7, 12, negative 4, plus the number of faces, 6. So negative 4 plus 6, that equals 2. And as long as the angles between the edges and the interior angles between faces all are equal, and the faces themselves are all the same, the answer will always be 2. And basically this means that there is no unit to the number 2, but it just, because it is constant for all the regular polynomials, it proves that there's a relationship between the different aspects of a polynomial. And the number is also, it also helped and expand the study of shapes and objects, and it was a huge contribution to geometry.
Okay, let's take a break from math and go into your personal life. So, as you can all see, Mr. Euler is blind. So could you talk about how you work with that?
I was 31 when I went blind. I lost sight in my right eye, probably because of a fever, people thought. And so it continued to grow worse as I did more and more intense cartography at St. Petersburg. And 28 years later, a cataract was discovered in the left eye, and I went fully blind. But it was the best thing ever that happened to me. I can still do math, I have less distractions by looking around, and with the help of my scribes, I am able to create more papers faster than ever before. So it's a blessing, I believe.
Wow, that's impressive. Okay, well, so you already talked about the Königsberg problem, but are there any other mathematical problems that you solved?
Well, I solved Basel problem, which is stepping stone in order for me to become recognized. It is something nobody could solve, even my mentor. The problem is that the sum of an infinite series of the reciprocal of squares of natural numbers, and the problem is that how do you discover sum? So basically it's 1 over 1 plus 1 over 4 plus 1 over 9, right? Because 1 squared, 2 squared, 3 squared. And so I found the answer to being pi squared over 6. I can't truly prove because it's infinite, right? How do you observe infinity? But I pretended that it would act in the same way as a finite series would act, so where there's a start and an end. I compared the two, and I was able to demonstrate how the answer worked numerically using the series. My theory was officially proven a century later by Carl Weierstrass using his factorization theorem.
A friend of mine is a structural engineer and he uses your column formula. Could you describe that column formula?
Structural engineer? Interesting. Pass me this bridge for a second. The column formula basically allows you to calculate how much force any of these beams, for example in this paper bridge, any of them can withstand before they buckle. Basically the formula is F, or the maximum load, equals N, which is conditions for N. So example here is connected and connected, so the factor would be 1, times pi squared times modulus of elasticity times moment of inertia over length squared, the length of the beam. That would give you the amount of force. And it is used in everyday civil engineering for any beam, support, pillar, anything. You can find it in a house on this lovely paper bridge, which seems to be very strong. Whichever boy built this, my seal of approval. This is used in civil engineering, in structural engineering, like the studio we're in right now, and it is used to prevent earthquakes, all sorts of things. So if someone were to cross the bridge, I would say go ahead, it's a safe bridge.
Okay, so what other contributions have you made to calculus?
Well, I have made many contributions. My work has aided calculus in its growth, in trigonometry, logarithms, functions, etc. I help create and popularize the f of x, which is a function itself, right? So I help popularize tan, sine, and cos ratios, which are very important, which you can use to calculate angles in the bridge beams. And I was able to create my identity theorem, which connected 5 of the most important numbers in all of math into one summary equation. And I also helped popularize sigma notation, which played a role in Basel problem.
Okay, so what about your societal contributions?
For one, there is column formula I derive, and also there is imaginary number of -1. It doesn't truly exist, but it is used in some of the most important things. Pretend this here is a control tower for plane, and here's your plane, right? The air traffic control will use imaginary number in their calculations to figure out where a plane is at any point in travel. Here, here, wherever. And it is used because if you use real numbers, you will calculate where the plane is here, but by the time you're done, it will already be here. And so the imaginary number is also used for pendulums, right? So there's a big building in China, Taipei 101, use the pendulum to counteract wind movement on the bridge or on the building. And so the pendulum moves opposite to the pressure of the wind, and they have to use my imaginary number to calculate how fast pendulum should move, which direction, etc. I also aided cartography and topography with the Königsberg problem, infinite sums with Basel problem, and geometry with the polynomial formula. And so I've been able to give your society a deeper understanding of some of the most complex issues in calculus by practically applying them.
Okay, well, I'd like to thank you again for speaking today, Mr. Euler, and I hope you have a great day.
You too, comrade.
Юрий. Немедленно прекратите. Секунду.
Я вообще не понял, что это такое?
Мы знаем...